All right. Well, thanks everybody. Like I was briefly mentioning, this is a talk more on exoplanet transit observing and some of the stuff that I've been doing recently. I'd say, I don't know, maybe February or March of this year, I decided I wanted to get into exoplanet transit observing, and basically that's when I started. It was about February or March of this year. I took a course with the AAVSO as a non-member. I'm not a member of them, but it was for 65 bucks, I think, and it was a 6-week course, self-paced essentially, but you did it as a group with other people that signed up for the course as well, and it basically walked you through a guide on how to do what I'm going to walk you guys through tonight and give you some information on. So if you do want to do this, I highly recommend at least walking through their material, which is free online. I'll show you where that is. But also taking that course is good, because then there's an instructor that you can ask questions, and they give you sample data, and there's YouTube videos to supplement along with that, that you can't get unless you take the course. So, all right. So before we jump in, oops, oh, I'm already advancing too fast here. Before we jump in, I didn't want to just completely assume that everybody knew what exoplanets was and transit. So I got 1 or 2 slides. It's just going to really high level hit on what an exoplanet transit is and the detection method and so forth. So a transit, like you've heard so many times, it's when a planet passes directly between its star that it's going around and the observer. And I've genericized it that way because we're on Earth, and we observe transits of exoplanets going around other stars, but we also observe transits of our own solar system planets going in front of our own star. So transit's kind of a generic term. And an exoplanet transit, which is what we're talking about tonight, is when an exoplanet, or a planet outside of our solar system that goes around a star other than our own, passes directly between us and the star. And when we observe that, we monitor the level of light of that star, and as that planet goes in front of it, there's a very subtle slight dimming of the star amount of light that we can detect and quantify and plot into what we call as a light curve. Some basic information. What can we know or understand or learn about the planet itself through these light curves is deeper curves, so that the amount that the light dips suggests that it's a larger planet than other smaller planets might create a not as deep of dip. And longer transits, the longer it takes to go across the star, suggests that the orbit of that planet is larger. I'll show this animation as I'm talking through the rest of these. Hopefully that is playing for you guys. So you'll see on the edge-on view, which is what we're looking for, planets that have the unique orbit that they go right in front of the star for us, plots that amount of level of light of the star. And we can understand what the planet itself size is, the orbit size is, and if we know the period, which we can easily also understand by multiple observations, once we start to see a pattern, we can understand what the period of the transit is. We can understand the inclination angle. So it may be directly edge on with us, which is 0 degrees, or anything above or below that, would be an oblique angle to us, but it would still be going across at least a portion of the face of the star from our perspective. Transit method is by far the most widely or successful detection method that we have to date. There's some other methods which I'll cover in my talk next week. But this one by far has been the most successful in terms of number of exoplanets that it has discovered. And the nice thing about it is you'll see, and that's why I'm able to do this, is it takes very reasonable and amateur equipment to be able to detect these exoplanet transits. So you'll see at the end, I think I included where, you know, NASA has a program where they're looking for other amateur astronomers to do this data collection for them and have repeated observations of candidate planets that may or may not be yet confirmed, so that they can do future research. So they're looking for help, and the reason is because it's very expensive and difficult to get time on, you know, the big NASA and professional telescopes. This helps them build that case with this data that you provide. Once we have those parameters like radius of the planet, the orbit, and other things, there's other detection methods. Not what we're going to cover tonight, but other detection methods that then can give us more information about the mass, the density, the composition, potentially, and even get maybe clues about its atmosphere as well. Then a little bit more information on the light curve. Now this is, I know this is probably not readable, this legend I have up here, but I just wanted to point this out. This is a light curve that I did recently on exoplanet, I think it's TRES 3b. And I just wanted to point out some of the anatomy of this curve so that when we get into the details here, this is the final result. You'll know where we're going. Essentially, we're measuring the brightness flux of the target star. So the target star is the star that has this exoplanet or suspected exoplanet going around it. And we measure the brightness of that star, and then we also measure the brightness of comparison stars, or what we call comp stars, in that same field of view that ideally are not variable stars, because they would also then be dimming or potentially dimming. We want steady comparison stars to compare against. And the idea is, you know, there's so many factors that can, you know, create noise when you're trying to measure the brightness of a star, like light pollution or clouds or smoke or anything that might get in the atmosphere in general. All can have effects on the brightness of the star. But the theory is, if your comparison stars should also be impacted by that same amount, whatever that noise may be. So if little, you know, cirrus clouds go overhead for a couple observations, relatively speaking, those should dim by the same amount as your target star. So you can still do this differential photometry analysis that is essentially what we're doing here. The curves that you see here, this is my raw data, the blue dots here. The next curve is fitted to a theoretical model of what, once you plug in the predicted transit time, the predicted planet radius, the orbit, the period, and so forth, it generates this model, which is the line, and then it fits your data to that curve. And so you can see in this case, it actually fits quite nicely and had an RMS of very, very low up here. It's 0.005 essentially. And then the remainders are here. This is just the error of my actual data versus the model. And then I chose, you can choose as many comp stars as you want. I just chose to show 3 comp stars. Can you see that they all stay relatively flat and do not have that dip? So you know that it's not just an anomaly. And then this last curve is kind of there just to make sure that you don't, you know, to know that you have good data. Essentially, this is a plot of air mass, which is the brownish, more smooth curve here. So as you're either, when you're observing the planet, you're either looking through, you know, gradually more and more air mass, or less and less in this case. The total flux counts of your comp stars should correlate with that as well. And so for the most part, you can see that it mostly does. And so this dip here, I'm not sure exactly what that is. That could have been a temporary cloud going through, and you can actually see potentially a little bit of error in that same time frame. So it helps you troubleshoot when you have issues. All right, so that's the quick overview of exoplanets, transits, and where we're going here. This is the final result. The rest of the talk
Jeff,
here.
I have a question there.
Yeah, what's up?
So, what is the time scale for that picture you just showed?
Yeah, so that's a great question. I'm going to get into that a little bit. It's what we call BJD TBD or TDB. Sorry. Let me hold that question because I will get into that. But essentially, time is essential here, and where we are in space, because we're on Earth and we revolve around a star in a very wide orbit. We could be on one side of the sun versus the other, and there is a considerable difference in time when we would observe this event, right? So we use this barycentric Julian date, and I'll get into more details there. But hold that thought, and then when I get to that, if I still haven't answered your question, let me know. So I tried to keep this fairly high level and break down the steps that I take into these 6 steps. Some of them I'll go through really quick because they're very similar to what a lot of us already do in our astro imaging. So let me get started here. I'll just jump right in. So the biggest difference, or one of the places I spend a good majority of my time, besides plotting and analyzing the results, is choosing your target and planning your target. On any clear night, it takes me I'm getting pretty good at it now. I probably can do it in about 20 minutes or so. Say, hey, it's clear outside. Let me go see if there's any transits that I could observe, looking that up, and then getting all the information and preparing for it before I actually physically go out and set up my telescope and so forth. So there's 2 things or 2 ways that you can figure out whether or not there is a exoplanet transit coming up that you would be able to observe. The first one is this NASA Exoplanet Watch program. So this is not, I don't think this is all that old, but every day you can go to their website, this Exoplanet Watch, and they have suggested targets by time zone. So you can see here for Central Time Zone, I think this is for tonight. They're suggesting that everybody go out and observe this and submit their results for this. Now, I don't know, I haven't researched the background on this one specifically, but often the reason why they're recommending this is because there is somebody or some team that is preparing, a deeper research project or wanting to just learn more about this to help inform the research that they're doing. And so they're helping they're asking the amateur community to help with that. And so that's what often influences the targets that they choose. And then, like I mentioned before, the other reason why they are looking for this is because they need help gathering some of this data. Some of these are candidates. They're not necessarily confirmed planets yet. And getting more and more observations will just help get it to be a confirmed exoplanet. So this is the real easy way. You just go to this website. They already have done all the work for you, and they give you the name of it. You can click on this, and it gives you more details on what the more specifics on that exoplanet is.
So Jeff, so they only recommend one exoplanet, or is there a list?
For each day, they only recommend one because on any given night, a transit can take anywhere from an hour to 6 hours. right? So you're probably only going to get one in a given night.
Yeah. Okay.
So the other method or way that I go and find out, if there's any candidates, so is this NASA Exoplanet Archive, and it is just a giant database of you can see here confirmed planets, exoplanets, and then they also have Kepler or K2 candidates, so ones that are suspected exoplanets and not yet confirmed. And then they have even added now TESS, which is another mission that's doing exoplanet research, test candidates or object of interest, they're calling them. So you can search all of, I always search all. I put in my latitude and longitude for my house here, and then I give a date range and a time range of, whatever, an hour after sunset to, an hour before sunrise the next day. And you click the predict events, and it takes a little while, but it essentially will give you a laundry list of possible candidates. Now, this one I have filtered. This is the results of what you would normally see. This is only showing one, but most of the time when I do that search, I'll get 100 or even more potential. I then take this list and I filter through it because I don't want to try to observe exoplanets that have a 0.001% dip in light, right? I would never be able to detect that. Even though it is, obviously a transit that is observable from my location, I'm filtering those out. I also don't want to look at stars that are super, super faint. So I also filter out, anything that's 14 magnitude or even fainter. I don't even bother, at least for now, because I'm just trying to get, more successful transits under my belt before I start to test the limits of my system. And then from that point, I go and I look and see, when is the event happening? When is the ingress or the start of the transit happening? When's the midpoint and when's the end or the egress? And I look at this because I want to see, well, is it too close to sunrise or sunset? And then also just what time in general, because I do like to sleep as well. So I try to find ones that are in a reasonable hour. And also then I look at transit duration, but again, unless it's longer than the observable darkness that we have, I don't worry too much about that. Then it has just some other parameters here, like it gives you the period and then the RA and DEC, which is you're definitely going to need when you do this. So let's go through this demo. I mean, I'm going to be demoing the software and stuff later on here. This TRESS 3B is our candidate for tonight. I did this search and this is the one that we arrived at. The next thing that I do is I have to collect a bunch of different data, and there is a worksheet that was provided from Dennis Conti, who is probably, I don't know, he's very, very much involved in the exoplanet program, if you will, with the AAVSO. And so he has his own website, astrodennis.com, and if you go there, he's also wrote that course that the AAVSO gives. So if you want to do this and you want to look more into this, definitely go to astrodennis.com, because his whole website is essentially dedicated to a lot of the stuff that I'm going to show you tonight. And this worksheet is one of them. This is his template, and I've since modified it. Can I ask that everybody go on mute unless you have a question? Thank you. So this worksheet is something that I downloaded from his website at one point, and I've since now made my own little tweaks to it, but essentially the format is still his. And it's very helpful. I do this for every transit that I go out and observe. And one is just to collect basic information about the exoplanet and the time and all that stuff. But then it's also just a good record to keep if you ever need to refer back to it. The sections in yellow are my way of indicating this is the bare essential information that I need to collect to be able to observe and go out. And the orange sections are stuff I need to go populate and go figure out what it is, like the radius of the star and the temperature of the star for modeling the transit light curve later on. But it's not something that I need immediately to go out and observe the planet or exoplanet transit. And then the stuff in blue is also stuff you need later on, but in this case, this is just my camera information and my location information, which for me doesn't change. So I've populated this once and I've never had to change it again. And then the green sections are just formulas. So they're using some of this other data to spit out some results here. But essentially I go through and I populate at least the yellow cells in preparation. And what it does is I have formulas over here that essentially, if you looked back at the exoplanet archive, it does everything in universal time. And so I don't ever want to make that mistake of converting that. So I convert it back to local central time, just using the spreadsheet, so I never have that issue. And so this gives me my start time of imaging, which you want to start imaging approximately at least 30 minutes before the exoplanet transit begins, because the beginning images serve as a baseline that you're going to normalize to. You obviously want to measure or image throughout the transit, so beginning, middle, and end. And then you want to continue imaging at least 30 minutes after the event. And again, the reason you want to do the 30 minutes before, 30 minutes after is, one, you need that data to normalize your data later on, but also, the timing that Exoplanet Archive suggests is just a predicted time. It's not, it could be off, a minute, 2 minutes, who knows. So you want to make sure that you don't miss the actual transit. So for that reason, you want to start imaging at least 30 minutes before and after. The other stuff here, there are websites that I don't know if I provided the links yet, but I will afterwards if people are interested. I've got a whole slew of links that I have now saved as favorites, but there's some other setting or information you're going to need, one of which is these limb darkening coefficients. And this is where my expertise or knowledge is pretty thin, but essentially there is some physics or phenomena that occurs as the exoplanet is transiting in front of the star at the ingress and egress, right? There's some other physics happening where it's not necessarily blocking the amount of light equally as it would when it was, completely covering the star. And so those areas of the curve need to have these limb darkening coefficients. And so there's a website that I just go to. I plug in the star radius, the star temperature, and some other parameters, and it spits out these coefficients for you. So this is the Exoplanet Worksheet, and this is all stuff that I do before I even go out and observe. So is there any questions yet on choosing your target and planning for your observing session? All right. Yeah, no, Jeff, how much lead time do you get? I mean, can you do this days ahead of time? I mean, oh yeah, Dennis. So that, remember back in this field here where I put in the date and time? Right. You can do this, a week in advance. Ah, okay. And actually you can use this as historical too, right? You can go back in time. Okay. And do a search and say, well, when was the last transit, for this? So this can be a research tool as well, but yeah, you don't need to do this. Yeah. Okay. So it
doesn't make for a busy night. Is, in other words, you can do all this planning days ahead of time.
You can. I mean, I've gotten to the point where I'm getting pretty good at it, and I'm not very, I'm a procrastinator. So, and also you don't know when it's clear, right? So I kind of just do it the day of, if anything, the afternoon when I know it's going to be clear. It takes me about 20 minutes, I'd say, to do this search and then populate this worksheet and make sure that I'll be able to observe this. One thing I didn't mention, but it kind of goes without saying a little bit, is the right ascension and declination. One of the other things that I do when I'm choosing my target is because I don't know my way around the sky from RA and DEX, so I plug this into SkyX or whatever your favorite planetarium software is, so that I know where in the sky this is. Because I want to also try to avoid anything that's too low or going to be setting too low during the transit time. So it's just one more thing that I quickly research to see where in the sky it's going to be. Also, if you have trees where you are or some other obstacles, you certainly want to make sure that those you're not trying to see a transit that's going to go into those places that are obstructed. So. All right, so we have.
So Jeff, I have one question.
Yeah.
Can you go to that the Exoplanet archive where you described about the criteria in choosing, right?
Yes.
So how do you choose? Like I think the transit depth is that what you mentioned, like the dip in the lighting.
Right. It's a percent of light dip, if you will.
Okay, so say it's 2.7 means it will dip by 2.7%, right?
Correct.
And you filter based on that?
Yes. That's one of the first things that I do, is I want to make sure that it's actually something that my meager equipment is able to detect.
So what would be a nominal value, like 1%?
So yeah, I think 1% is a good nominal value. I have not found the limits of my equipment yet, but I did observe a 0.5% successfully so far.
Okay.
So right, I don't know how much lower I can go, but I know I can at least observe a 0.5% dip, which is pretty good, I think.
Okay, thank you.
Yep. All right, so we are moving on to collecting the data. And so this is just a picture of the telescope that I use. It's very similar. This is where I won't spend a ton of time talking, because it's, a lot of us are already doing astrophotography. So all of the stuff that you do for that, you're going to do for here. Framing your shot, auto guiding, dealing with pure flips. Everything that we do for astroimaging is applicable here. I already mentioned the imaging 30 minutes before and after the event. Exposure times. So the exposure time is something that you need to figure out experimentally before the event begins. And so one of the first things I do is, after I get my telescope set up and polar aligned, and I've got my auto guider calibrated, I immediately go to where my exoplanet is going to be, take some test shots, and I measure the saturation of my target star, and I'm aiming for about 75%. That way, if the star is rising, I have room so that it won't get saturated, and if it's going down, I at least have enough signal that it won't get too dim, or I won't lose too much of the signal after it starts to go through more and more air mass. Preferably, now I have not done this. I started out right off the bat using a V filter, which is one of the suggested filters that you use. It's just a known scientific range or spectrum, or whatever you call it. I use the V filter, but any of these, the UB, V, RI, Johnson Bessel filters will work. And in fact, it's possible here, if I continue to do this more, I will buy a second filter that is different from the V, because it's going to be something that you need to have when you're trying to differentiate between what is truly an exoplanet transit and just an eclipsing binary star. Because an eclipsing binary star would also give you this effect of light dip, and it could be confused as an exoplanet transit. And so when you do that, you observe the transit with two different filters, and you should see the same effect regardless of the filter if it's truly an exoplanet. Whereas if it was an eclipsing binary, it would not be the same.
So, Jeff, do you have a handy a transfer plot of what the a V filter looks like?
I don't have it handy, but it's essentially very close to our green filters.
Oh, okay.
Yeah. Some of the other things.
Did it fit?
Yeah.
Some of the other things that are a little bit different than what we usually do is that I do not dither my images, meaning I don't nudge the scope, up, down, left, right, a couple pixels.
Yeah.
Can you somebody go on mute, please? There's some feedback coming through. Thanks. So I don't dither my images. We often do this to help with our astro images and provide cleaner data when we process them. We actually want the star to fall on as best as possible the same pixels to minimize pixel to pixel variation that may throw off your data. So I do not dither my images, and auto guiding helps keep the rest, that star centered on those same pixels. And then the other thing that I have running in the background on my computer when I'm doing this imaging is I have time synchronization software. So every 15 minutes, which is probably more aggressive than it needs to be, but every 15 minutes it checks online and says what's the accurate time, and then it updates my system PC time to be precise. And the reason why, obviously, you want to make sure that you have good system time is because when you're going to share these results or upload them, they're looking for fairly accurate timing of when the ingress started, or more importantly, they're usually they want to know when the midpoint of the transit is, because that's more consistently easier to track. And then, just like you would with our normal astro imaging, I take darks, flats, and bias calibration frames for each observing session. Well, obviously I reuse darks and biases, but I do take flats after each observing session for later on when we process this data.
Jeff, can you explain why you often do 2x2 binning? Is there a reason for that?
I do it because I don't need high resolution, right? There's no advantage for high resolution. And frankly, I'm just trying to get a shorter exposure time so that I can take more images and get more data points. Mm-hmm. So for me, I don't need the 1x1. In fact, I would say exclusively now do 2x2 as my starting point. And unless, that the star is just so saturated, then I would bump it down to a 1x1 to help with the, prevent saturation. But there's just no need to do the 1x1.
Cool.
So this is just a zoom in picture. I have my QSI 690 camera with a built-in auto guider. I have a moonlight focuser that does the auto focusing for me. Inside the housing here is all my filters. So I always use the V filter, and then I have a reducer flattener on this particular scope, the Celestron, and this is my C11 Schmidt-Cassegrain telescope. So if you're interested in the equipment, this is, essentially amateur equipment. So that is the collection, collecting the data and your calibration data. One thing while you're doing this though is you're gonna, you know, I mentioned I wanted to make sure, one, I'm looking at the star that we're interested in, and I also wanted to make sure that it wasn't oversaturated. I needed to determine what my exposure time was. So this is that TRES 3b exoplanet that I'm observing. Here's my image. So which star is my star that I want to look at? I kind of want to make sure that I'm, one, looking at it, that it's in my field of view, and I know which one it is, so that I just know later on when I go to process this, I can remember what the heck star it is, because all I got right now is all little white dots. So there's a couple things you can do. This is actually the star that we're interested in, but I put those there. There is a variable star plotter, which is free to use through the AAVSO. You can go to and I'll share this PowerPoint later on, but you can go to this website, click here, you put in the RA and DEC, and then tell it what field of view you want and what chart you want, and you just hit plot chart, and it spits out a nice little chart like this. And so the crosshairs here in the center is my exact precise location, and that's my star. So this, I now know I can use this as a tool to match up with my image, to make sure that, one, that I am looking at the right star. But then also what's neat about this is later on when we choose our comparison stars, it's giving me the magnitude of some of the stars in this field of view that I can choose. And you'll see, actually I didn't point it out, but in that worksheet, once you enter the magnitude of your target star, it gives you a recommended range of magnitudes that you should choose as your comparison stars. And so that's where this is also very helpful and why I do this. So this is our star that we're going after. It has, you know, these couple nearby stars that kind of make a triangle. You've got this arch kind of or this curve of stars, and then this cluster. If I bring back my image, you can see here's that curve that I pointed out. Here's those 3 stars that make up the triangle, and then here's that cluster. So I know I'm in the right area. I'm in the right neighborhood. I'm ready to go and start my imaging session. And so now it's just a matter of, you know, I use Sequence Generator Pro to control my equipment, and I just set it. I say, hey, take, you know, 1,000 images of whatever exposure I decided using the V filter, and just keep going. Now I can get more fancy and tell it to shut down and start imaging, but I usually start my imaging session. I do, or I will go to sleep, and then as long as I know it's not going to rain or anything, I'll just let the rig run until the morning, and then wake up and shut it down after the fact. But essentially, that's the steps that I take to collect the data, the calibration data, and make sure that I'm looking at the correct star. So we've chosen our target. We've now captured the data. Now it's actually time to process the data. Pre-processing is just like we do for astroimaging. You use your bias, darks, and flats, and use those calibration files to correct your light images or your science images. And I use AstroImage for this. You certainly could use any software that is capable of doing that type of calibration. But the reason why I use AstroImage, for one, is it's super easy. It's very similar to what we've seen like in PixInsight. You know, you choose your lights, bias, the locations of them. But the reason why, the primary reason why I use AstroImage is because the timestamp when we collect the images in the FITS header, it puts universal time. or it may put local time, but it does not put this BJD TDB time, which is that barycentric Julian date time. And I think I have a slide here. Actually, I don't. I'll just briefly explain it. But this, while you're doing the calibration of the data, it actually goes and amends the FITS header of each file as well. And it takes the timestamp that it was in there and it adds a FITS header parameter in there that is this timestamp. And this timestamp is then used later on when we plot that chart that I showed you, because that's actually the x-axis of that plot. So you're almost, unless you have a different way of adding that BJD TDB timestamp, you're almost, you almost need to use this. So I don't spend a lot of time talking about this. This is pretty straightforward. You fill out, you go through these, select your files, tell it to create a master flat, master dark, master bias, add these, the timestamp to the FITS header, and I hit start, and it takes, depending on how many images you have, 1 or 2 or 3 minutes or so. It goes through pretty quick. The other thing I'll mention, this is give a little plug, is AstroImage is a free program. It's free to download. And so for anybody who's even doing astroimaging or astrophotography and doesn't want to buy PixInsight just yet or make that investment, this is a very effective and free alternative. We usually point people to Nebulosity. But even Nebulosity, you got to pay, 40, 50 bucks or something for. This is absolutely free. So if you're just getting started, this is certainly a good solution, I think. So
Jeff, do you do unique darks and flats for every exoplanet?
No, I have a library of darks.
Okay.
Yeah, if you're trying to do this with an uncooled camera, you're probably going to have to do your own darks and biases every single session.
Right.
But with those of us that have cooled cameras, we have that luxury where we can build a library. I have had to build more, or expand my library, because honestly, I wasn't really doing hardly any 2x2 binning imaging until I started doing this, and so I had to build out a 2x2 library, and then I think I have different increments that I normally would have otherwise chosen. Like, right, I have 30 seconds, 45 seconds, 60 seconds, and 2 minutes, I think, is all I have. Whereas, often we do, 1, 3, 5, 10 minute, 20 minute, much longer intervals. So that's pre-processing. It's really straightforward. I'm not even going to demonstrate that, but there is, back in that astrodemis.com website that I mentioned earlier, in his website, he has a very detailed, it's 50 or 60 pages long PDF that walks you through line by line, step by step, exactly what I'm doing here. So I didn't want to get into too much of the weeds in that area, but if you want to know more, I certainly go to his website and read that. And actually, that 60-page document is essentially the AAVSO course that I took. That's the text that goes along with that course. All right, so we pre-process our data. We now have calibrated light images, and we're ready to finally perform the differential photometry on it. This is where I'm going to get into more of a demonstration because it's just easier than doing slides. So I'll actually show you how I do this. But essentially, before I dive into that, I wanted to just give you some quick terminology here. So when we're doing photometry, I think this next slide, there is an inner circle here called the aperture. So everything inside the circle is what we're going to measure the star brightness from. And then there's this outer annulus here. There's a gap between the two, right? And this measures the sky background surrounding the star. And so when we're trying to measure the brightness of the star, we want to actually subtract any contribution from the sky background. So that's why you're measuring this outer perimeter, and you subtract this from this inside to get the true brightness of the star that you're interested in. So you have to figure out what that size of that aperture is, what the size of the annulus needs to be, and then there's some other things that you got to plug into AstroImage-J about your camera specifically, what the gain is, what the noise is, and so forth. And then you select your target star, which is, in this case, is T1, and then go and select your comp stars. And I chose these. You can choose 1, 2, 3, 4, or as many as you want. I think 2 or 3 is usually customary. And you're trying to select ones that are at least similar in size physically, because they also use the same aperture and annulus. So you want to make sure that the star doesn't go outside those regions. But then also ones in that range of magnitude that I mentioned earlier. So these are the ones that I chose. And once you've done that, you hit enter, and AstroImage-J does all the work in seconds. And it builds this giant table, which is more or less just a spreadsheet. It spits out the results, and then I save that immediately, because that's essentially the data that I'll work from for the remainder here. So before I get into the demo, one other thing was, now that we have, AstroImage-J has done all the work of performing the calculations. We do have some other inputs that we need before we can do the plotting and analyzing of the results. One I mentioned is this BJD. Oh, hang on, I didn't go through that. I did skip over that. Let me just go back to this, because I know there was a question on it. So the BJD TDB time. I'm going to just try to explain it in words, and then when I send out this presentation, this link gives you a very in-depth explanation for it. But essentially, we are on Earth, which in itself is moving, going around a star, and this, our solar system is essentially moving relative to whatever target star that we're trying to observe. So we're a moving target. But the real big difference is us going around the sun. Depending on the time of year that we're trying to observe a transit going across the star in some direction, we could be on one side of the sun, and then 6 months later we're completely on the other side of the sun. And if we were trying to observe that event from one or either one of those, the time that that event would happen could be as much as 16 minutes off. And that's because it takes 8 minutes essentially from the center of our solar system to where we are in our orbit for light to reach us. And so 16 minutes is a big deal when we're trying to measure the timing of these events. And we want to make sure that we're picking a location, relatively speaking, that has less error than from planet Earth, which is orbiting around this star at a huge distance away from it. So the point that we pick is called the barycentric center of our solar system, which is not the center of the sun, but it's the center of the sun and all the planets. What that point, that center of mass, that all of our planets orbit around. And so that's the barycentric center that we all normalize our timestamps to, that location. And the TDB, I'm trying to remember that portion of it. I'm not even going to begin to explain this, but where the TDB takes into account relativity and the speed at which we're moving, right? And moving clocks move faster or slower and so forth. And so that portion, the TDB portion, corrects for that effect as well. So now that we're all talking from a given point of time, from a common location, and we're adjusting for the time dilation, right? These now, my results can be shared with other amateurs that are doing the same thing. Now you can get technical. Yes, the whole solar system is moving as well, and so forth. But the effects of that is much smaller than the Earth going around the sun.
So Jeff, what is the, okay, so what is the, how many decimal points, what, I mean, what's the, essentially the precision of this time?
So I can tell you that when I take my local time and then I convert it to this BJD TDB time, it's a difference of about 4 minutes.
Okay, but my question is you said that this TDB takes in relativity.
Right.
Yeah.
I get it.
And that's going to be in the picoseconds.
Potentially, you're probably right. I think this is just the common chosen time so that we can all compare, right? You're
okay.
absolutely right. And actually, when you go to this website that gives a much better, frankly, much better than what I just explained, but more in depth, you can have BJD universal time. You can have BJD whatever time you want, right? The conversion time, but you got to be careful that you don't compare one to the other. That isn't all in the same. This is essentially your units, right? So if you're going to compare directly, you want to make sure that you always specify BJD, but then also the time domain as well, which in this case is this TDB. But you're right, absolutely. The precision here is probably far more than I need at the amateur level, but in the professional community, it may not be.
Right.
And I think this is, I'm just observing transits, so it's on probably a much bigger scale. But when you're starting to observe, other things where they're wanting to know more about the atmosphere and stuff like that, I think that this timestamp becomes much more and more critical because they're trying to measure things at that exact instant of the transit rather than just the transit as a whole, So hopefully that answered your question on the time scale and what's on the bottom of the chart. I tried my best. It starts to get a little technical there. All right, so after I got us off track there, the whole reason I went there is because before I can analyze my data or plot it, I want to convert from that exoplanet archive. Remember the results it gave me, the predicted ingress, egress, and midpoint. Well, all those times were in universal time. And so I want to convert that to this BJD TDB time so that I can plot that on my chart. And so there's a website for that. I'm sure there's an app for it too. But I go to this website. I first convert my local time to universal time, and then universal time to BJD TDB time. And I then populate that on my worksheet just so I have it for reference. And I'm only interested in the decimal portion of that timestamp, because you'll see in the chart here we're only looking at it on a scale. So then I enter that. So in this case, the predicted ingress time stamp in this BJD TDB was this 0.66333 number. The egress was this 0.7 number. And I plotted those, or I plugged those in here. There's some labels here that you can, this is just free form text fields that I populate. In this case, this was a screenshot when I was doing WASP 93B, just not too long ago, September 2nd. I put my name, my filter, and this is just the titles of your chart. And then this section down here is for controlling your x-axis and y-axis scale, right? So you want to try to fit all your data on. For the most part, the auto range works pretty good, but there's often where I want to now manipulate. Once I get the data on there, I manipulate this, and so this is where you can really control your chart. and then the size of the chart too. I didn't get into it, and I won't get into too much detail, but meridian flips are inevitable. Sometimes you're going to be imaging a transit through a meridian flip, and so for that time, when your telescope has to flip over and reset itself, you obviously can't image during that time. It's usually not that big a deal because a flip takes minutes at most, and then you can just continue your session. But when it comes to analyzing the results, now your images are 180 degrees out at some point. And so you need to tell Astra Image J when that happened. It doesn't know when that happened. And so you have to specify that. Fortunately, most of the transits that I've been observing, I've been able to do without having to do a meridian flip. There was one that I did, and it's just an extra step. You got to tell Astra Image J when it should flip. This section down here is remember I told you we start imaging 30 minutes before and 30 minutes after, and so this is the section that uses those lead-in images and the trailing images to normalize the data. And so these are the same numbers, at least initially, as when my ingress and egress was predicted to be. And so this multi-plot main window is the main window that I use, and kind of the control center, if you will, for plotting. The last thing that, if you didn't already do it, I pointed out this earlier, but if you didn't already go get your limb darkening coefficients, this would be the time you need to do that, because we're going to enter those here soon. There's a website that I can link to later on, where you plug in the star radius and the temperature, and it's a theoretical, it just spits out the coefficients that you need then. So you need those. All right. So finally, we get to some demo, because now it's just going to be easier to show you rather than do slides. All right, so this is Astra Image J. It's a very simple Java-based program, and I hope this is not too small. I apologize if it is. If this is the screen resolution of my screen, but these icons on the right here, Astra Image J or Astra Image is I think a tool that's been around for quite a while and has been used for a long time. They then amended it, or somebody took it and added this J to it and rewrote the program to add these functions on the right hand here for exoplanet transit processing. And so everything that I use is in this right hand side, this over here, but it is much more powerful program than what I'm even using it for. So the first thing I do is I need to open up my light images. And so I import an image sequence. And here is TRES 3B. Here's all my light frames. And I only have to select the first image in these 64 images. And it'll tell me, hey, I found 65 images. I'm going to start with image 1. I'm going to do every one. But you could, say I had a transit that lasted for 5 hours and I took a 60-second image. You may not want all those data points. You may say, just give me every third one. So you can control, what sample points you actually load. And so once you're happy with that, I load it. And so now it loaded all of those 65 images. And the first thing I do is I go through them and I try to weed out any bad images, like this very first one. For some reason, my very first image it looks like guiding issues or something, or I bumped the scope or something happened. And so I want to get rid of this one, and I've got double stars everywhere here. So the cool thing about Astra Image J is you can just click that red X, and now that has excluded that one from this data set. Now I'm down to 64 images, which you probably can't see it, but this is 1 of 64. And then I just scrub through the images here. Oh, now there was one here that for whatever reason there looks like star bloat, or you know, I'm not sure if that would cause me any issues, but I'm going to get rid of it because I don't need every single image. And then I just scrubbed through the rest of this. What I'm looking for is any obvious, you know, star satellite trails, or the other thing that I'm looking for is making sure that the images are not shifting around too much. Because if they aren't aligned, then there's an extra step I'm going to have to do to align them first before I do my differential photometry analysis. But these, fortunately, are all pretty well aligned. The stars are barely even moving. So I think there was one more bad one out here at the end that I just didn't want to include in my data set. So I'm happy with that. I'll go back to the first image here. And this is, now remember, these are the raw light frames that I gathered. So I would do, and I'll just demonstrate it. I'm not going to actually process it, but the, actually it's over here. The data processor. This is the screenshot that I showed you before where you specified your bias, darks, flats, and all the other stuff here, and you would hit start. And it goes through pretty quick in a couple minutes, or even less actually. It will spit out your calibrated files in a subdirectory of your choosing. I just use the default, which is this pipeline out. So let's go there. Actually, let's close this. And now let's reload or import our calibrated images. So here's that directory pipeline out. Again, here are my images. It looks like I did not exclude those to begin with, so I'm going to load all 65 again. It says 60, actually 64. Just quick get rid of that guy again. And this guy. All right, so now we are, now we have to figure out what our annulus and our aperture size needs to be. So here's our target star, and AstroImageJ has a utility that helps you figure out that really quick. If you hold down the Alt key and just click the star, it generates this full width half maximum curve for you. And you can see I definitely did not have a saturated star. It was only getting up to 35,000 ADU. I probably could have even gone a little bit longer than, what was this? 2-minute images, right? I could have gone longer, but I was happy with 2-minute images. But what it's telling you is that 7 pixels is what you should set that aperture to. And then your annulus, the inner diameter should be 13 pixels and the outer diameter is 20 pixels. For those of you guys that do image, you do your astro imaging, this is also, I don't know if there's another quick tool, handy tool like this, but if you're imaging, you know, something like M42 or something that has a really bright star or bright region or area in it, you might want to, you know, think about pulling this up. I think PixInsight does a similar to this. Gabe, you might know, but it's just a really handy way to know if a star is saturated. All right, so 7, 13, and 20 is the settings I want to do. So I'm going to click on this little set icon, and it's already set because I did this ahead of time, but I would type in 7, 13, and 20, and that sets the size of those, or the diameter of those rings. The other information that's already in there for me because I've done this, but if you were doing this for the first time, you would have to enter, is the gain of your computer, your camera, the readout noise, and then the dark current, those parameters. And then these aren't absolutely required, but I have them in there, is that if a star reaches 45,000 or 55,000, it will give me alerts in the log that certain stars reach that threshold. It won't error out, it just will give me a warning that it came close. So now that I've set the size of the circle, now I can finally go do my analysis here that AstroImageJ will do. So this little icon here is perform multi-aperture photometry, which is what I want to do. It's just confirming again, are these the settings that you want? Yep, those are, actually I want to start with image 1. So change that. And I want to go to the last image, which is 62. These are the diameters of my aperture and annulus. Everything else I just leave here default, but I did go through, initially and made sure that the right ones were correct. And you say place apertures. So finally I get to select my star. So here's my target star. You always choose that one first, and then you can choose your comparison stars as you see fit. So I'm just going to choose 3 real quick. And once you're done, you hit enter. And you can see it chugs through the data pretty quick because it's just measuring the brightness. And once it does that, you get all kinds of windows to pop up. So this is one of the things that I don't like about AstroImageJ, because I don't have a screen big enough to display all these windows. So I'm constantly jockeying around windows here so I can see things. But when I hit enter, it went through and it measured every single one of my target star and comp stars for every image. And it went and gathered all this data here. And the ones that we're interested in and going to be plotting is this relative flux of T1, our target star, as compared to the sum of the relative flux of the rest of the comparison stars.
Jeff, can I ask a quick question?
Yeah.
So you set up that annulus, that bullseye thing for your primary or your target star, but then you use those same numbers for all of the comp stars, or
yep.
Is that just an assumption that all the comp stars are going to have the same annulus? And
yeah, so it's a great question. So earlier, if you remember, I said when you're choosing your comparison stars, there's 2 things you want to consider. One is that it's in that range, recommended range of magnitude that was on my earlier chart. But exactly what you're hitting on, you also want one that is relatively physically in size similar, because you're right, this could fall outside if I chose, even though the star might have been in the magnitude range, it could fall outside of this and give me, some error or introduce some error. So yeah, certainly you want to choose comp stars that are similar in magnitude, but also similar in size.
Similar in size, okay.
Yep. Yeah, good question. So there is a tremendous amount of data here. Frankly, you don't even need to look at any of this because AstroImageJ, takes all this data into account. But what I do is immediately when it generates this, I save this as a spreadsheet essentially, so that I have it later on. Now because we're doing a demo here, I'm going to close this stuff, and then I'm going to reopen it, loading the data that I did earlier. So I first need to load my, oops. One second here. There we go. So on that multi-plane main plot, I'm going to load my data set, essentially my table of results that I did a while back. And by the way, this is, if you're interested, this is my file structure. This is what they recommend through that course that I took. Obviously you have your data, but then there's a single folder where you're keeping all your analysis data. And so this table is what I saved when I did this initially. Okay, not sure what that is. Hopefully that won't be an error. And then I load, because I saved it, a plot configuration file So when I was done and I plotted my results, I saved that configuration so that I could quickly pull it up later on, which is what I'm doing here. Yes. Oh. Oh. Did I say save or open? I think I said save, didn't I? I might just screwed that up. Okay, we're good. All right. So normally you don't have this table. This nice, pretty looking chart is not there yet. It's blank with nothing in it. And you have to go to that main plot file or window. And this is where I mentioned you enter your ingress and egress times that you got when you converted it to that BJD TDB timestamp. You'd then copy those same to your normalized range. And then I do, you know, I just started adjusting the x-axis and y-axis. You play around this until it starts, you start to see your data. Again, at this point, you're only going to see your blue data here. And then I go over to this data fit. This is the window that creates this model, essentially, this line, this curve. And I enter in the period of the exoplanet, which is what we got from the NASA Exoplanet Archive. When we searched for that, one of the fields there were the period. And then you can enter in any one of these parameters here and the rest will auto update. I typically enter in the stellar radius in terms of solar radius. And so this is a 0.82. So a little bit smaller than our sun is the star that we were looking at. And that auto updates, and this tells it, you know, the spectral type of the star. And so that's an input to the model that happens down here below. And so the good thing is that all this stuff is green, which means it's happy. The other thing that I do is I add those dark or limb darkening coefficients. Remember that I said you got to go out to that website and get those coefficients. This is where you enter those. And so when you do that, it then, because the rest of these are default settings, it goes out and it starts to plot and draw this curve for you. Now this is also an area where I want to learn or know a little bit more about. This is a little bit more math than I'm familiar with, but there are these things called detrend parameters, which I think are ways to adjust your data and fit to this curve to better fit it. Frankly, I'm not entirely sure. But the rule of thumb, or what they taught you in that course, is that you can easily turn them on and off. And if you watch on the left-hand side, you'll see the data change slightly as you turn these on and off. And you want to use detrend parameters if it makes this BIC value, which I don't know what that is, but it's some parameter, maybe somebody else knows. If it moves by more than 3 units. So for example, right now it's 156. If I turn on the total C counts parameter, it only goes to 155. So it's not a good detrend parameter or something that's significant. If I turn on this BJD one, it doesn't change it all that much, so I didn't have it on. And I didn't have a meridian flip, so there's no reason to turn it on. The only one that I'm using is this air mass detrend parameter, and actually that didn't even move it that much either. But this is one area where I want to learn a little bit more what I'm doing. I'm just kind of clicking buttons at this point until I see this BIC value not change much anymore. But nevertheless, that's what you do to help fit the data to your curve, or fit your curve to the data, and vice versa. And then this section down here plots the error. And so you can, you know, change these settings here as well. If for some reason the Y or the X axis wasn't displaying as nicely as this is here, I would then go back to this area, this XY area, and adjust those. You know, you can adjust these up and down, left and right, to make your plot more presentable. The last thing is adding your comp stars. And so this gigantic window here is, I mean, you know, I'm probably going to change this, but every one of these rows is data spots from our table. And so you can see when I ran my analysis, I actually chose 5 comp stars, or is it 6 comp stars? 2, 3, 4, 5, 6. So 5, I guess. And so it has the ability, I could plot, I could turn these other ones on, and it'll do that. But I chose to just use the first 3. But this column right here, these are just on-off check boxes that can turn on and off your comp stars. And you may, actually I do this, I do look at all the comp stars, and some comp stars are better than others. You'll see when you go back to this plot that, oops, some may have more spread than others. And so you may not want to use some of the comp stars in your data set. And if that's the case, they have yet another window where you can deselect or turn on and off your different comp stars. And so you can see here I had my comp star C5 and C6 that I turned off. I didn't include in my data because they were not good comp stars to use. They introduced more error to my analysis than what I was looking for. So I opted to end up not including those ideas. But that's kind of why AstroImage is so powerful, because it literally is just turning on and off these things, and in the background it's reperforming all those calculations for you. So this is where you plot your target curve, whatever comp stars you want to select, you turn on. Over here, the other thing that you're going to use a lot is the shifting. So you'll notice here that my target star has 0 shift. And so on this curve, it is right at the 1 marker. And so it's, obviously that's 100% light. It dips down to, let's say, what does that say, 97%, and then it goes back up to, relatively speaking, 100%. All these plots, if they had 0 shift, would be right on top of each other, and so it just does not be legible for this curve. So I then use this shift scale here to make it more presentable. So every one of these, except for my raw data, all of these are arbitrarily shifted down just to make the chart more presentable. That's all. But if I return these all back to 0 shift, then I would have to turn off, all but one to really be able to look at the graph and use it for anything intelligible. So what's left here? Now that I've gone through and I've loaded my data, I've plotted everything, I've made it nice and pretty. I made I have my predicted ingress and egress. In this case, they correlated very nicely. It's because this is a very well-known exoplanet, and we know a lot about it and the period, and so we can very accurately predict when the next transit is going to happen. So it's not surprising that my predictions matched my actual observed results. But on those test objects of interest or any unconfirmed planet, exoplanets that we're looking to get better data on, that may not necessarily be the case. Those could be off. And I have had 1 or 2 where I've had, they were significantly shifted, where it said it should have started up here, but I observed it actually happening later. I was a little suspect whether my timestamp, remember I told you I have time synchronization software. I wasn't ready to say that, my actual observations were that far off from the predictions. It's possible though, and I'm getting a little bit more confident now that I'm doing things right, that if that happens in the future, it will actually be legitimate, deviation from prediction rather than just an error that I made.
So Jeff, can I interject a question here?
Yeah.
Yeah. Okay. So one of the things that's confusing about this series of graphs is and this had bothered me from the first time you showed this, is why the error bars are plotted all by themselves and not around the data in the prediction curve.
Yeah, so it's because I arbitrarily shifted it, Dennis. So if I go here.
Okay.
I did that intentionally so that you can see the data. But if you want it on top of it, I can certainly put it on top of it.
Okay. So somehow that makes more sense.
Okay.
Oh, what's being shown in the magenta, that was a residual plot. It's when you subtract the two away from each other, right?
I thought it was like this point, the delta from this, and then it's putting error bars on either side of that. I thought that's what this was. So it's this deviation from the model fit.
Okay.
Okay. So,
but sorry to interject, but that point itself is a result from the true raw spectrum minus the sum of the other brightness, minus the sum of the other candidate stars.
Mm-hmm.
And that's where the error bar comes from those measurements.
Okay. See, that's the stuff that I want to get more familiar with, because it's, I haven't learned the details of that.
So Gabe, could you say that again? What the error bars are actually representing?
The error bars, from my understanding, I haven't done any of this, but from my understanding, is kind of captures the noise that's in the subtraction. So you take the photometry from the target star minus all the, I think you're using the sum or the mean or something like that. You're aggregating
the sum of
them.
Okay.
Minus the other stars. And for each star, you have that center spot and then the annulus that you have the subtraction from. And each pixel has this kind of Poisson distribution for how the photons come in. And I assume that's what's being captured here with this error bar, is that Poisson distribution, but it's rolled up through all the pixels inside the central spot, and subtracting all the pixels in the annulus. And you're doing that for one star, but you're also doing the subtraction for target star minus the sum of the other stars too. Mm-hmm. So each of those operations has this error propagated forward to this final kind of residual plot. That's my understanding.
So Jeff, can you remove that offset again? I'm trying to see where those error bars are around which data.
Yeah, it should lie dead on. Yeah.
So that's 0 offset. So it's dead on.
Okay, so.
And if it helps, I can let me shift that curve down just a little, get it away from my other data.
The error bars in the center of the dip around the actual data of the dip.
Right.
The magenta, from what I understand, the magenta are the red dots minus the red line, plus the error bars. Which is why when you look at the error bar points, they hover plus or minus to that magenta dashed line.
You know what, Dennis, what I can do, because I'm interested in this as well. Not only what this is, but what do we conclude from it? What is why is this meaningful, right?
Yeah.
Is this good? Is this bad? That's what I want to start to learn or better understand myself. But what I can do is I can create a better graph. I'll get rid of all this other junk. I'll have just this information on there zoomed in so you can see it better. And I can share that with you later on.
Okay.
The magenta is commonly referred to as a residual plot when you make a fit to data and then you subtract the model from the data. You get the residuals, and when you inspect that plot, you want to see if there's any sort of systematic undulation or bias in that data. And if there is, then there's another component that you can add to the model that would treat that effect. And in this data, there might be something a little bit before ingress where there's a rise and then a fall.
Right.
In the data, but otherwise it looks really good. It's centered around the data. It's not systematically high or systematically low, and it does oscillate, not oscillate, but it's pretty much random around that. And I think that's one thing.
That's what you want, right? You want it
exactly.
kind of evenly distributed, right?
Exactly.
Yeah.
Which it's kind of correlates here too, right? I mean, that's this air mass versus total seat counts, right? You can see I had something happening early on, and maybe that's what caused this part. But then for the rest, it pretty much trended as predicted, and so that's why this correlates as well.
Okay.
And who knows what this? There is another Slack group called Exoplanet Watch. It's the guys that run the NASA website that I belong to. They've been very helpful, and their thought when they saw this dip was that I didn't have my camera cooled long enough. So I've now since been making sure that my camera was well cooled for 30 minutes or so before I even begin to start imaging. But I hadn't always been disciplined in doing that previously. So I'm going to see later on, we'll see in future transits that I do, whether or not that makes a difference. So we're getting at time here. I'm probably longer than I wanted to be here, but hopefully that gives you a flavor for what it is I've been doing here and how I get to this curve and the plot and everything, all the steps I go through. The only part that I haven't shared with you yet is how to submit your results. And I won't demonstrate that, but essentially in Astra Image J, under that main plot window, there is a macro. Essentially, you go select it, and it says give me your measurement table, and it then spits out a formatted report. It's just a text file that you then can go to AAVSO's website, assuming you're registered there. It doesn't cost you anything. Anybody can register and get an account there, and you can upload your data. And so that's what I've started to do. And right now, at least as of tonight, I have 3 observations that I've contributed to them. And so my observer code is KJEB. And in fact, you can go to this website or go to this link, type in my observer code, and you can see all my observations. The other cool thing you can do is, let's say I wanted to go look at other people who perhaps observed TRES 3b with the one that we just did. I can type in that star name and I can look at everybody else's results as well. So, and this is all free, available to anybody. You don't have to be an AAVSO member. All right, so with that, any other questions?
I have a question. So you are using the C11, right?
The C11, yes. Yep.
So at what focal length you are actually taking the pictures, and how important is the focus?
So, okay, first one is, hang on, I think I have, I don't ever remember my focal length.
It was
But it's
1980 something.
It's 1955 is my focal length. So that
Yeah, so
essentially I have a 0.7 reducer on an f10 scope. That's 11 inches in diameter. So when you do the math, that's my focal length.
yeah, so how important is the focus actually? Because the stars are actually pinpoint, right?
Yeah.
And slight changes in the focus is actually can cause problems in these calculations, right? So
actually, the way I understand it is, and I believe what I read when I was taking that course is, if you are trying to observe a star that is just, even 1 second images are saturating, that they recommend you actually defocus to prevent that. And so precise focus is not critical for this.
that's interesting.
Yeah. Because I think all you're interested in is the intensity or the brightness, and whether or not
the
that's
change
in
in
focus.
brightness.
Yeah, right. The change in brightness. You're right. Relative change. And so I'm not even interested in the absolute magnitude or absolute brightness. I just want to know how it's comparing to the comparison stars.
So that's why you can actually bin for 2 or above, right?
Yeah, right.